Border Gateway Protocol is a standardized exterior gateway protocol designed to exchange routing and reachability information among autonomous systems on the Internet. BGP is classified as a path vector routing protocol, and it makes routing decisions based on paths, network policies, or rule sets configured by a network administrator. BGP used for routing within an autonomous system is called Interior Border Gateway Protocol. Internal BGP. In contrast, the Internet application of the protocol is called Exterior Border Gateway Protocol. External BGP. The Border Gateway Protocol was first described in 1989 in RFC 1105 and has been in use on the Internet since 1994. Ipv6 Bgp was first defined in RFC 1883 in 1995, and it was improved to RFC 2283 in 1998. The current version of BGP is version 4. BGP neighbors, called peers, are established by manual configuration among routers to create a TCP session on port 179. A BGP speaker sends 19-byte keep-alive messages every 60 seconds to maintain the connection. Among routing protocols, BGP is unique in using TCP as its transport protocol. When BGP runs between two peers in the same autonomous system, routers on the boundary of one is exchanging information with another as are called border or edge routers or simply eBGP peers and are typically connected directly, while iBGP peers can be interconnected through other intermediate routers. Other deployment topologies are also possible, such as running eBGP peering inside a VPN tunnel, allowing two remote sites to exchange routing information in a secure and isolated manner. The main difference between iBGP and eBGP peering is in the way routes that were received from one peer are propagated to other peers. For instance, new routes learned from an eBGP peer are typically redistributed to all iBGP peers as well as all other eBGP peers. However, if new routes are learned on an iBGP peering, then they are re-advertised only to all eBGP peers. These route propagation rules effectively require that all iBGP peers inside an IS are interconnected in a full mesh. How routes are propagated can be controlled in detail via the route maps mechanism. This mechanism consists of a set of rules. Each rule describes, for routes matching some given criteria, what action should be taken. The action could be to drop the route, or it could be to modify some attributes of the route before inserting it in the routing table. During the peering handshake, when open messages are exchanged, BGP speakers can negotiate optional capabilities of the session, including multi-protocol extensions and various recovery modes, if the multi-protocol extensions to BGP are negotiated at the time of creation. The BGP speaker can prefix the network layer reachability information it advertises with an address family prefix. These families include the IPv4, IPv6, IPv4, IPv6 virtual private networks and multicast BGP. Increasingly, BGP is used as a generalized signaling protocol to carry information about routes that may not be part of the global Internet, such as VPNs. In order to make decisions in its operations with peers, a BGP peer uses a simple finite state machine that consists of 6 states: idle, connect, active, open sent, open confirm, and established. For each peer-to-peer session, a BGP implementation maintains a state variable that tracks which of these 6 states the session is in. The BGP defines the messages that each peer should exchange in order to change the session from one state to another. The first state is the idle state. In the idle state, BGP initializes all resources, refuses all inbound BGP connection attempts and initiates a TCP connection to the peer. The second state is connect. In the connect state, the router waits for the TCP connection to complete and transitions to the open send state if successful. If unsuccessful, it starts the connect retry timer and transitions to the active state upon expiration. In the active state, the router resets the connect retry timer to 0 and returns to the connect state. In the open send state, the router sends an open message and waits for one in return in order to transition to the Open confirm state. Keep-leave messages are exchanged and, upon successful receipt, the router is placed into the established state. In the established state, the router can send and receive keep-leave, update, and notification messages to and from its peer. In the simplest arrangement, all routers within a single AS and participating in BGP routing must be configured in a full mesh. Each router must be configured as a peer to every other router. This causes scaling problems, since the number of required connections grows quadratically with the number of routers involved. To alleviate the problem, BGP implements two options: route reflectors and BGP confederations. The following discussion of basic update processing assumes a full iBGP mesh. A given BGP router may accept network layer reachability information containing